Hi, I'm Tim. I should get my slides up, but we're having some Mac and Windows confusion issues, so I'm connected to my home computer remotely right now. So I haven't really brought up the slides. So I go by Tim. My real publication name is Chi Hin Lam, which I'll show you in a bit, but that's my Chinese name. And I went to I did my doctorate at USC, University of Southern California in Los Angeles. That's how I got a bit into the white shop business. I'm mostly a data person. I deal with any data people want help, and I work for beer, food, and well, anything grad student related. Like that's I spent 6 years, 6.5 years there, mostly supporting different groups from Hawaii. There's pelagic fisheries research program, mostly Kevin Wang, John Seibert, a bunch of those guys. So I love Hawaii. Then I did quite a bit of work with Southwest Fisheries Science Center in San Diego, La Jolla. So there are a bunch of other groups I worked there. That Susie Cohen that was on Sharks, Heidi Delaware. Then also the IATTC, the Inter-American Tropical Tuna Association Commission, and dealing mostly with big eye and yellowfin tuna. And my PhD work was mostly on striped marlin and white sharks. Striped marlin was data collected from the whole Pacific. I didn't get the honor to go to those places, but I was stuck with dealing with most of the data that got back. And for the white shark work was the white sharks out in Guadalupe Island. So one of the three known aggregations. So you have San Francisco area, and then Guadalupe, and also South Africa, and also Australia. But like one of the few places with a white shark aggregation. So a lot of data comes from Guadalupe. And right now I'm with UMass Amherst, U of Massachusetts, and I'm based in Gloucester, Massachusetts. So if you've seen Perfect Storm, that's the town where George Clooney and everyone hang out, and where all the big fishing industry, mostly on saltfish and bluefin tuna. But right now, I guess the whole of New England are mostly groundfish. But that's right now I'm working on bluefin tuna and basically pelagic species of the Atlantic Ocean. And that's why I'm just switching between different oceans, handling different data. And a lot of things basically that I've come through the years is how people are dealing with data, stuck with the different analysis, and part of my interest is having different tools that you guys can use so to expedite that process. And a lot of times now we're having a lot more tools that we used to, but it's still kind of unclear some of the distinctions. And part of our philosophy when I first started developing and helping to write packages or softwares to let people use it easily. And that's why I do workshops like this. Most of the time it's just for a labor of love is what I do. And I know people can use it, but a lot of my time is spent in customer support. It's like people, it's like, this does not work. It's like, okay, try this, and this does not work. And so that's the hard part, but the good part is it allows people to do something pretty easily and kind of have the standard methods. So as I said, there are a lot of other methods out there. The methods I work with is one of the most popular ones. I think it's partly because we spend so much time in just talking to people and trying to get people to use it. There are other programs that I know of, which I probably touch on some of those, and you might want to try those later on your own too. But I'll stick to the methods that I work with mostly, and hopefully you can get a sense of what those are. So I guess that's the idea of the workshop. For the flow of the workshop, we'll try to work with some data set that Enrico has assembled for us. There's a bunch of good sharks data that he has, and I think he's willing to share it among the whole group. And I haven't seen the data too, so we're likely to get stuck. But that's the whole point. It's not an easy process. It's always a long process of trying and banging your head against the wall. But the good part is at least you're not in the field. So you can go for a coffee and come back and just deal with it later, or just get a new computer. so that's the easy part. So I would argue for the amount of time that you spend out in the field collecting data, you should use the same amount of time in dealing with your data in terms of just the basics, getting the right tools, knowing the methods, knowing what you're doing. I think that is almost as important as you go out and collect the data, because all these new methods, they're mostly a model, and a model means it has assumptions. So in order to know how to drive it correctly, you better know the models enough, if not like inside out. It's almost impossible to know it inside out, but at least you kind of know what you're doing and kind of know how to interpret your results with a grain of salt. Because it's still, a model is just a creation, it's a recreation of what's out there. It's a simplification, it's not perfect, but it's the best guess that we got. So I think that's one idea I want you guys to remember whenever you run any models, even just a regression model. It's the same. It's those assumptions that go behind it. So, and the workflow is, I'll try to go through some quick slides and run through some examples. I'll try to get you guys set up to run different things. I see quite a number of Macs here. There are two parts. The first one is a data management part, and that's done in Microsoft Access. So if you're mostly Mac, you might miss out a bit on that part, but that might not be too important. But like so what I do for my setup, I usually do boots. So Mac doesn't really have a good data management software. It's not like you pretty much have to write your own stuff to connect to an Oracle or other stuff. So Mac, I don't know why they ignore the data management side. But so I have to use Windows for that purpose. And basically Microsoft Access is in Windows, a part of the Office. And if you guys have dual boots, maybe that part can follow along. And the geolocation side, which are the movement models and such, is platform independent. So that part you can do it on Linux, Mac, or Windows, which I do on all three too. But I'll show it on the Windows side, but it will work just the same way on the Mac side. So I'll just spend some time just knowing each other, and because we're waiting, and also start to get some of the software on, and hopefully that should go smoothly, which is usually, I think, if I get through the software and able to show the presentation in the morning, then we're a success for the day. This is just an introduction to geolocation, which is the method that we need to use for any pad tag. As you well know, yeah, I probably will go through it, but I have to acknowledge my co-worker, Benjamin Gallerati. He has been doing similar work from almost as soon as I started working too. So he has been doing a lot of the similar methods and help develop and maintain some of the tools together. So yeah, there's basically two of us mostly maintaining. The earlier designers, we call them the Sage. The Sage, they have other projects going on, so we took over and maintain things so that it will keep working, hopefully for eternity. So I'm with the Large Pelagic Research Center. They're part of UMass Amherst, and as the name suggests, we're not focusing really on any one particular species. We work with anything that big and move and at least can employ people. So that's the idea. And that's the real name. My coworker likes to put my Chinese name on, so I don't get to delete it in this version. So that's it. So why use light? Because for fish that submerge or sharks that submerge, I always envy sharks because they do break the surface and you can use spot tech, and that makes the life a lot easier. But for fish like the bluefin tuna that our lab works with, stays mostly underwater, and you have to use light-based geolocation. And yep, on everything, highly migratory. The graphic that you see at the back is just a generalized movement of bluefin tuna in the Atlantic. You can see they cover most of the Atlantic with different movement into the Mediterranean. That's usually where they get killed. And sometimes some historic movement, and actually there are more recent movement back to Norway as the water warms up. There's an argument saying with global warming, you actually see the range coming up. And there's a historic movement that's lost that goes to South America, which we haven't seen it yet. It used to be, and I think in the 60s and 70s that used to happen. So when we're dealing with a species that covers such a large amount of ground, light seems to be the only option that we have right now. I know we have the geomagnetic tag coming up, but it's still somewhat related to light too. We still require lights to give you the longitude. So this is a typical light curve that you can collect from any pad tag that you use. When they collect the data in the tag itself, it will look like that. Different manufacturer at the end give you some output that does not look like that because you have the transmission issue and they have some processing in between. But essentially, you're just measuring. You're putting a light sensor, much like your phone, into the tag, and it records a continuous light stream of data. So this is one you can see when it's high up, it's bright, and that's daytime, and when it's dark, it's nighttime. And you can see the progression here that you have sunrise. So it's a progression. That's the steepest moving part in the whole entire record. So night and day is boring. So only sunrise and sunset, the twilight period, it gets interesting. Is this progression of gradient, and that's probably one of the reason why it works, because this is the two parts that we need to get, the sunrise, sunset. This sample data comes from a mooring in New Caledonia, so this thing is more to a mooring. So it doesn't move, it's the perfect condition. You have cloudy days, bright days, and that's probably some of the reason why you see this is not a fish. So how come you have like changes in your light level? It's because it could be cloudy, so it would reflect in what you see here. And don't ask me what this is. Maybe the moon come up like this. But yeah, there's this degree of variation, and you can expect if you put it in an animal, this thing will get even more complicated. So this is the ideal case. So you have sunrise, light coming up, and then sunset. And to do the basics, you can look in between. The middle point of these two curves is the noon. So just very easy to distinguish. And you have timestamps for your local noons. And you can just easily convert it to the times here usually is GMT. So once you have that time, you can basically put yourself anywhere around the world, because with each degree of change in longitude, that's 15 minutes. So if the world go around in 360 degrees per day, and so you get your noon will come up at different time steps. So you can basically get longitude from that way, just from the noon time. So that's one piece of information to take out. And then the second piece, I do not have the graphic here. This is the length of the day. So as you know, when you go towards the north and south pole, the day length will change. So that will allow you to distinguish where in latitude that you are. So the length of the day is what gives you latitude. And that's basically what people do, even in not prehistoric times, in early times of navigation. Sailors use the same information. You have to come up with nodal noon, and that will give you longitude. And you can just also observe, they didn't use day length, but it's using a declination. So that will allow you to have an angle, which you can do a bit of just simple calculations to give you latitude. And essentially what we are doing in the text are doing the same thing. It's like having these different information and apply these formulas. Yeah, so don't worry about too much all these things. This is kind of the standard thing. You can have many ways you can get the same calculations done. You can just Google solar day length, or just, yeah, there are plenty of things that do that. And one of the most recent applications is for the solar panels. You know how solar power is getting more popularized and people can install the solar panel at homes. They're actually using the same equation to calculate how much energy they can get out from their solar system. So similar stuff. And but the problem with these things is light has quite a bit of error. The most obvious case is when you have equinox. Equinox means everywhere on Earth will have the same amount of daily. So everywhere is 12 hours. So twice a year you have the equinox. And when that happens, using light does not give you any information at all in terms of latitude. So you still can get local noon, but you can be anywhere from the North Pole to South Pole. That's equinox. That's the power of equinox. And hang on, come back. And that's basically, this chart shows kind of the effect of the equinox. So you have, these are the two times, one in March and one in September. That will be the problem. And don't worry too much about the colors, but essentially you can see how what error that you have from around those period of time, you can almost put yourself anywhere around the world. And this is just a matter of different degrees of error and bias. So the idea being, once you're near the equinox, you lose a lot of ability to tell where you are on this world. And that's just the limitation of light geolocation. So if you actually have done, if you look at sort of, I'll go back to my problem later on. But basically, some of the popular instruments for this type of application include the microwave telemetry tags. So this is just a generic pad tag. You guys know it pretty well. It has the light sensor in the nose cone, and this is one of our setup here. And it also works for the archival tags with the light stock sticking out. So Wi-Fi computers, low tech tags that are archival tags that most of the tuna species use, especially for the tropical tunas, they use these tags and use the similar methods. This will be the light sensor will be somewhere here. This part will stay in the fish. Oh. Okay. So that's the newer types I mentioned with desert style tags. I don't know if you guys have you played with the desert style tag? Yeah, it's hard to get it to hit probably, isn't it? It's used on explosives. I have one that exploded on my lab. In the right orientation, like I was worried. It's like if it's not in the right orientation, it could be pretty painful. But so that's the desert style tag, and they do mix geolocation. They have lights that provide longitude, and for latitude they use magnetic fields. So magnetic fields, you have the field lines, the map. So it's almost like an sea surface temperature matching, but you're matching towards the magnetic map. So they have magnetometer in it, and tag also has the 3D accelerometer sensor, so you probably will see some talks in the Shacks International about that. New Hampshire actually loves to use these guys. And so that on your lab is the X tag and standard tag, and that's the new tag from wildlife. Okay, so we're still working on moorings, and you'll see. Okay, so we were just zooming in on 1 day of the mooring data, but essentially, if you keep the tag out for long, you have this continuous light curve. So you have day and night, day and night through time. And this part is another unknown. Like, why would you have kind of a baseline of like night data here, and somehow this thing just drops off? Like, the mooring is not diving, so I don't know what happened. Okay, so that's the real. So this tag, you see how it's nice and continuous. This is sampling at every 1 minute or 2 minutes. So that's a continuous time series, and with this temporal resolution, you can get very nice data. But usually when you get the transmitted tag, that's the data that you're working with. It's the same way of plotting it. Essentially what microwave or wildlife are doing, they're trying to pick out the part with the most changes. So it's basically, you're trying to cut these parts out into here. And usually they do a pretty good job, but you never know because that's all you get back. And so that's some of the challenges that you deal with. That's a drifter. This is a drifter data in the Pacific. So this pad tag was floating around on the drifter buoy, and that's what I collect through Taiwan. A lot of the time you're just dealing with this data set. And there's another case. So this is a big eye tuna. And there's something funny about this graph. So even though it looks the same, day and night actually is reversed because that's the fish behavior. So big eye tuna, they love diving during the daytime. So what you see here, these parts are likely to be daytime. It's because they just like the behavior will change what you get from the curve. So knowing what species you're working with matters. And the good thing for big eye tuna, and actually they're the best tuna to work with, is they are just like a clock. You can actually look at when they dive, you know it's night and day. They're better than any text that you have because they just operate like a robot. And I love big eye. Okay, so. And this is the other type that you deal with. That's the microwave setup. All it does is just to take the timestamp of sunrise and sunset. It doesn't even give you those few points in between, but they just tell you a time. It's, they work very well for shark species, and any shallow sharks or billfish will be perfect because their sensors are very good at getting light out from shallow layers. It won't work too well for deep diving tunas like what we have. It's almost very, very challenging, but in a shallow water setting, this thing is pretty accurate usually. And so on the top is, I think this, so this usually is just one line. This is sunrise or sunset time. So essentially you have the two sunrise sunset times, and in between will be a noon time or midnight. So it's actually the same thing that I showed you from that schematic, but all they transmit back to you is just this type of data. And you can see the times that they cannot pick out what sunrise, sunset, and the smoosh in between makes your geolocation processing a lot harder. And okay, so when you're lucky enough to get an X tag back, so that's microwave telemetry tags, they actually give you the light curves too. But the sensor of the tag matters. We were looking at the other light curves from wildlife computers or low tag. Their sensors are more sensitive both at the top and the lower end. So they don't get cut off or saturated that quickly. But for X-Tags, their purpose is to get sunrise sunset times. So they don't care how bright or dark it is, but it only reaches the threshold, it gets cut off, and you can see that effect here. So you're supposed to have continuous, like, see clouds or no clouds, but here it just I know it's daylight, that's it. So that's the cutoff. But you might still get that resolution in between, but it makes a lot of fitting some standard models harder. Because like the models I deal with, they're thinking about continuous light instead of this is more like a boxcar setup. So on and off switch makes it harder to do. So knowing kind of the data, you have to use different methods essentially, and the range of methods that I'll try to get you guys to use tackle different aspects of these things. So if you have the ideal case, you have the continuous light curve, you can use the the best model. But in between that, those in between cases that either the behavior makes it harder to use the most complex model, you can just go one step below and get something out first before you attempt anything harder. And that's what usually I would do too. Like when it's good to get these data back like that, but you still have to pick the right scale or right uncertainty to choose which model to use. Otherwise, you just get stuck pretty quickly. And it's not a bad thing to have something simple to work first, and then go to harder stuff. So that's one philosophy. It's like you build the things from the simplest, and then keep going up. Instead of us usually get aggressive and want to get the best thing to work first, which usually won't work. So that's my lesson through the years. Oh, yeah. So that's basically the Mykonos, the effect of Mykonos, and you can see anywhere it doesn't have any distinction in terms of latitude you can get from the Mykonos. You guys get to play on this website. This is pretty good. They have pretty maps of which in what time of the year you get what day night through the world. So you can see on any non-equinox period, you have a very nice distinction for day and night. There's a curve, so some place will get daylight earlier, some place will get daylight later, even in the latitude sense. Oops, okay. So, where am I? Come on. Okay. So, that's the effect of the raw data. So usually raw data, once the manufacturer calculates positions for you, it likely looks like this. I think this is a bluefin tuna that we have. And the bluefin should be taken up somewhere here, likely to go north or around here. But for the different behavior, time of year, and area in between, you're likely to get positions in the South Pacific. The fish is not flying. You get positions up north, and that's usually when you get these erroneous positions when you're near the equinox. And the methods that we're dealing with is trying to use this type of raw data and make sense of where the fish goes. There are quite a number of different methods out there. There's kind of a quick summary. Yeah, the most popular stuff right now is called state space model. Essentially, it's just basically it's a statistical framework saying you have some observations and you have an assumed movement model. So you're trying to balance what you know the fish might be behaving and balance it with your observations, knowing that there's error and bias in between. So it's almost like a weighted average between the two things. And the good part is, at least some of the simple movement model, it can be a correlated random walk, or it can even be just a simple random walk. They are pretty good in describing the general sense of the movement of animals that we deal with. And then you mix it in with your real observations to kind of just add that layer on top, and your final results is a balance between the two. So that's essentially what state space models are. And there are different approaches to get to that, which I've almost stepped through some of those. Those that I've dealt with is Lucid and Cyber early work, and they are the common filter model. So common filter is a classic set of filters or models that was first developed, if I remember correctly, mostly for missile tracking for Navy. So essentially, we're tracking a missile, right? A White Shot is like a missile. So using the same ideas. And then there are some newer methods, Patterson, Summers, or Fowler Jensen. They're using more the MCMC, so Markov chain approaches, and they're in Bayesian framework. So our common filter framework and then the Bayesian framework, there are different ways of doing it. But essentially, it's still a space model. You're trying to balance the two sorts of information together. You have your underlying movement and then your observations. You're doing that. And then there's the non-state space model. So Trimley et al. I know some sharp researchers use that one. I've talked to a few of them. It's probably a good model, but like what I've heard so far is like it's very tricky to use. So it's hard to use it yourself, other than getting, I think Jan Trimley, I forget his first name, but to help you out. And so that's how when I hear people saying that, then they're asking whether I can help with their data, so they can just kind of run through the two things together. So one lesson from that is it's good to shop around for your models and see if they say the same things together. It's hard to say who's really doing a good job if you don't have a double tag data set, but yeah, you want the best scenario is like all the things point to the same general directions. And some of the limitations right now for space, like even space models, they are limited by your data input. So your observations, if it comes in daily, so you have positions observed from the animal comes daily. Personally, I wouldn't trust anything that will go below that scale. So there are times people will say they can do hourly positions based on observation comes in daily, which, like for me, I don't see how you get it. Like, you probably can do it, but how much I trust it, I really don't know. And at least from the little thing I know about, say, Trimley, I've seen some of the presentations that actually I can't make sense of the tempo scale. It's like, your pet tag seems to be recording hourly. How come, daily? How come you have almost hourly positions? Like 30 days of record, I see like more than 30 points on that graph. So something I don't really understand. And yeah, so just simple things like that. You want to pay attention. And what I was mentioning about space-based approach, there are different ways of fitting the model. So even just using maximum likelihood, or just using Bayesian one-color type. So the end result is the same. It will still give you the similar answer, just a different approach, statistical approach to getting your model set up. And the good part of a space-based model, usually we come up with some error estimates and confidence region, because it's a model, so there's a way to describe your uncertainty around your estimates. So that's a good part. And most people won't show that uncertainty estimates in the final publication, but if you don't have that big a data set, I do encourage you to show the confidence region, because the best scenario for any light-based method, if I remember correctly off the top of my head, longitude-wise, you have an error between 0.1 to 0.3 degrees in error, but that's the best. And for latitude, it's about 0.7 degrees. So if you multiply it by 1 degree is 16 nautical miles, that's still a lot of error, even in the best case scenario. And that's not accounting for any error in the measurement. That's just the theoretical limits. Like how accurate can you get with just using light data? So that's the amount of inherent error you deal with. So if you ever get to publish your data in a nice short format, do try to show your confidence region. And some of the other approaches to lightweight geolocations, like, okay, if I have more than light, can I use some of these auxiliary data to help us to ground truth some of it? And that's why I mentioned about using magnetic fields. That's what the manufacturer is doing. But popular approaches, the most popular one is definitely sea surface temperature, because it's easily available through different web services. You can get those images pretty daily. Global scale resolution is pretty good. It may not work too well for coastal environments, but it's getting better. You can also use model outputs of SST. There are plenty of satellite products that are simulated with GUI data and try to come up with just a grand oceanographic models. You can even just use Navy models, NCOM, SciComm, whatever, to use as an input. But that's the most popular ones. But other things that people have used include salinity tides. Coastline bathymetry is also helpful just to keep the fish not walking on land. Sharks may be walking on land because you have Sharknado, so I don't use bathymetry for that one. But yeah, and that's the other things that you can do to ground truth your data. They're not ground truth, but help a lot. Okay, so these models I won't get to cover, but essentially just give you a quick preview. Molecular computation is actually my boss, and one of the former postdoc, Francois Roer. He's actually a very competent and famous Frenchman that works on these methods. And if you use Argo's common filter stuff right now, he's the one who wrote that algorithm for the Argo CLS. So he's affiliated with CLS, and once he finished his postdoc work with Molly, he actually went back to CLS and get them to incorporate that common filter model for your spots data for the Argo services. So that's why he's part of it. He's working on his own now as a big data science guy. So we'll make a lot more money in that sense. And so the data set that this paper was dealing with is the sunrise sunset times. So what if you just have the most minimal number of data points, which is the sunrise sunset times? Well, what can you deal with? So this model basically take care of these things and factor in bathymetry and SST to come up with improved geolocation. And so these are the approaches. So there's non-Gaussian, and there's the iterative filtering and smoothing that allows him to do it. And if you purchase the CLS option of processing your tag for any pet tag, which is, I think, sells you at 800 euros per tag, they will process that tag with this method for you. So that's the track and log services that they give. So it's essentially using this the method from this paper. And then there's Michael Summers, one of the earlier basin work that also deal with light data, and he used the Bayesian framework using Markov chain Monte Carlo. His stuff is also as an R package. You can get to it pretty easily. There's a French group that basically shows how to use his package, because somehow his package is not that easy to use. So a French group actually published a paper on using the package, and you can go to that paper and look at the setup. So I guess the good part for Bayesian framework, you have to supply priors. So priors are prior assumptions, reasonable assumptions for the animals, and it's tricky because like different people work with different animals, so that's why I think they make the paper out of this is to give some reasonable priors for what to use. And so there's MCMC, and that's the package being trip estimation. And Yeah, it's good stuff, but it just takes some time to get used to. I'm not an expert on this one, but at least I think it's a good package. Yeah, so that's the price that the other French group tell you each of those options and what you're supposed to use for those numbers. There's a whole page of these things, so you have to sort through those. And don't ask me what would change if you change all these priors, like all these a whole list. And I guess with each parameter that you change, you might have a different output. So I haven't really gone in depth into knowing how changing each of the parameter will change your tracks. So that's the problem. That's some of the issues. Like when you're doing a model, like changing the inputs may change your stuff. So you might want to spend time to know, kind of do your own sensitivity analysis in a sense.
Sorry, so it means that those guys are saying that the priors of this model are not based on the species, are based on the method, right?
Both. It's like this, like the methods will incorporate, like say, swimming speed. Then it will be based on the animals, but how, like the other stuff, like what's that lane, turning angle, things like that. That like
general in terms of method.
Yeah, so like so it's still based on reasonable assumptions, but there are options like let's see here. Well, like mean speed over 12-hour time variance and distribution, things like that. Like, like unless you do experiments to collect this, it's still guesswork. Like you can do reasonable guess and guess something to work. So I'm not discounting that, but you just need to have some knowledge of what's out there. So this group, Ufei, Martin, Hendrik, these are the smart guys in Denmark. So if ever you go to the Danish Institute, they actually have the best group for analyzing fish movement. That's non-spot tag related. So these guys are really good at doing acoustic tags and pet tag too for this one. But their methods was developed mostly with COD. So COD is small archival tag without light sensor in it, and they were using tidal and the changes in tidals. So there's a tidal geolocation method. But essentially, they were able to use a lot of the good models in the North Sea to supply for the input data. But essentially, it's still a hidden Markov data, and it can do behavior switching. So it will incorporate whether the fish is moving or stop, and that's the good part about this set of methods is you can incorporate a number of different behavioral states. So that's another products from not just the track, but you get a distinction whether that might be a resident base or a moving base. And that comes in the MATLAB toolbox. I know Martin's trying to adapt it to R, but he's a busy guy, so I don't think he's working directly on it right now. But if I know he's working, I'll let you know. Okay, so for me, I've been dealing with this set of methods. Anders Nielsen and John Cyber. Anders also from the same Danish group, but he was doing a postdoc with John, and that's how I met them up back in the mid-2000s. And this method, why it's special back in 2002 is because most of the time we are dealing with what manufacturers have already provided, so it's already a lat long. But these guys went back to the raw data, the light curves, and do a method based on the light curve. So you're going from, instead of relying on somebody, you do everything from the ground up. And that's why we like that method. And let's see. Okay, so I'll just simplify our models and all call the common filter models, KF. Yeah, so the idea to do a common filter model is we want we want to track of geographic positions. We want to know the uncertainties, and we'll get some quantitative movement parameters. So that basically describes whether your animal is moving a lot or not moving, whether your raw data has a lot of error in it. So we want to have an idea of those and allow us to compare between tracks, at least for the same species or same group of animals, if not across animals. Okay, so the basic setup. The basic setup, the tag records 3 data streams at least. You have depth, temperature, and light. So that will be on your top part right here. And the manufacturer software will give you a raw position. They'll interpret that data stream and give you lat long. So that's this stage. And the easiest model is run, we call KF track. We'll just pass through these lat long positions and pass it through a simple counter filter model. And that's KF track. Will give you an estimated track based on that. Then the next upgrade is we use sea surface temperature to help us along. And so you do start with the same basic data. Use your tag record temperature, and if it hits the surface, you have a daily value of sea surface temperature. So your input data set now become not just lat long, but SST. So this is, we call it KFSST. They just add sea surface temperature matching to help you along in interpreting your positions. And then the last one, which I was alluding earlier on, is called Trackit. So it works directly with the raw data stream, be it depth, temperature, and light, and just deal with it that completely instead of going through that intermediate process of this path. Like you skip all those and just go directly to Trackit. Like for our workshop, we probably we'll try some of these at the end, but if it doesn't get through, it doesn't hurt you too much, because it's the same framework. You actually, the workflow are very similar. So if once you get through KF track, KF SST, it will get you to track it pretty easily, and we'll run through some examples to get to first the idea. Okay, so that's the data again. So this one, so this one just give you, for mooring data, we have this kind of estimate. So I forgot where the mooring is. Let's see over here. But that's what we get. So it's a mooring that is supposed to be somewhere here, and there's certain error from the light data, so that's the best we can get. And we have a cloud or uncertainty around it that describe how the model sees that the possibility within that cloud. So again, so we have an estimator of the track and describe the uncertainty, and you can track through time the degree of error. So the good part is, like, your start and end point usually. So your start and end point without error, but through time, you see how the error just increases. But when it's near the start and end point, since you know those 2 points are without error, the models just kind of converge back on again. So it will grant your track according to the start and end point usually. I'll just show everything here. Okay, so the underlying similarities include, so they will use a random walk with drift and affection. So you have 2 components. You have diffusion, that's just random movement, and you have affection, so drift, it's like directed movements. It will include observation error, predict and describe observations error at each position. It uses the common filter. It doesn't matter which variant that they use, but essentially the common filter. It uses the maximum likelihood framework, and at the end it will give you the most probable track, we call. It's a weighted average of what is observed and what you predict, and at the end is like a complete description of the whole process. Right? With that process called like the common smoothing is taking care of the entire track and we estimate all at once. And the difference is, so for these methods, KF track or KFST or KFSST, they need lat long, and Trackit, it uses light, and then you can use sea surface temperature on these method, and that's just the common user framework. It doesn't really matter. It gets technical here. Okay, so just one slide on unreadable symbols. So what this slide basically shows, okay, so don't think too much about here. Essentially here you have north-south movement. So this is north-south, east-west movement is accounted in the model. Those two parameters are called U and V, and UV, when we combine UV, it will be alpha, so that's part of the model. And then you can see, oh, sorry, this is position, but this is the UV. And then it has some error, there's Gaussian errors, and that's basically how you describe it. And the Gaussian errors is related to diffusion. So this is, the diffusion is this circle. And the process also includes bias and errors. So biases is systematic error, we call it bias. And then we have just error here, that's the error term. So essentially you have affection, diffusion, and then bias and error in the model. So those are the parameters that the model estimates. There's a handful of them. Let's see. So this is some examples we'll probably get to running it. But this is a quick output. So your input track looks like just a flat file, and your model, when you specify a model, you can turn options on and off, which we'll get through, so I won't spend too much time here. But this scenario is just saying that you don't give any confidence in your observations at all. So ignore all the geolocations. So what that happens is, you know the start endpoint, and it draws a straight line through when you don't give any confidence at all to your observations. And you can see how you have the same kind of cloud of uncertainty. You have a more narrow cloud at the start and endpoint, and it's just reflected in both longitude and latitude. So that's the idea here. And yeah, and these are the parameters that you can work with. So you have the affection part, you have the diffusion part, you have bias in longitude, bias in latitude, error in longitude, error in latitude, and this is these two parameters relate to the error structure of your observations near the equinox or not. So there's a term in the equations itself that will give you an error structure of what you expect to see. You can the one that usually we turn on is saying that you will see more error near the equinox. So that's just how it describes. So these two parameters allow you to describe it. It's a function of date. So like whether you're close to a certain date, your error will increase. So those two parameters describe it. Okay, so this is the second scenario. I think what we did here, probably still the same. You don't trust it, but you specify a more or less error and ask it just to run it with that one. So you're actually specifying how much error in the data, which usually you let the model estimate it, but you're allowed to just say, okay, I think I only have certain degree of error in my track. You can set and do that. Okay, so yeah, so this will be what you okay. This is probably what you get from running examples. Is this type of track that will include yeah, I don't know why when we put this together we spell everything out. Like you don't have to spell everything out. It's all you can just use the default and let the model run. So there are two steps to running a model. You have to specify what you want to estimate or not. When you don't estimate a parameter, you keep it fixed. So you essentially assign a value to it. But usually we'll let everything estimate through the model instead of fixing it. But you can initialize it. So you can put it, you give some values to initialize the model. The model has to start somewhere. So imagine that you're actually in a map of solutions. But how to get to the final solution depends on where you start. So sometimes if you put it in the right place, if you don't put it in the right place, you'll still end up in the right solution. But some situations, if you put it closer to the endpoint, then you have a better chance of getting the model to converge and work. So I think that's the headache part, because there's so many ways to get to the solution, but whether you take the right path to the solution may change it sometimes. And so for this estimate, we can see there's a so the beginning and end point, there's no error. I think that's showing latitude error, and in between you have more error towards in this part of the track, and then it just decreases, and then at the end it knows that it has to drop back to 0 because those are the known standard endpoints. And so you see here you have the parameter estimates, and that's the standard deviation of that estimate. So essentially what it's saying here for this guy, error in longitude, like 3 degrees error with a standard deviation of 0.4, and then for latitude it's 2.1. Actually, so this guy is very non-typical. It's usually you have more error in latitude than longitude. But yes, at least that's what it says here. And then, so this is just an example showing with SST on. Did I show one without SST on? Yeah, this one is without SST on. So once you fit it with SST, you can see how the SST right now, and this is probably what we'll run through too. So yeah, there. And once you include SST, you can see how the error drops for that purpose. So that was the light-only estimate, and now once you include SST, the error decreases maybe at least by 0.5 degree, and you can see how you have now an estimate of how well you fit to the SST data. So now you're just increasing parameters. So we start out with the SST. We don't have the error in SST and also in radius. For radius is how far you search for in the neighborhood for the right temperature. So you can, instead of looking for the whole ocean, you look at somewhere around your track estimates. Okay, so yeah, this one we'll go through anyway. So there's just some recommendations. There's a maximum likelihood framework, so we have convergence. We said we need the model to converge in order to be happy about how the model performs. Sometimes you don't get to the model to converge because maybe the model is just too complex. So when that happens, what we usually do, we'll turn off some parameters. So that's when that happens. So that means we're not estimating everything, and just keep it fixed either as 0 or a number that you specify. So essentially here, what we do, we turn off the bias. So instead of cutting out the error into bias and error, we just say, okay, just lump everything up into the error term instead of a systematic error. And so we just turn it off at that point. And that might help you to get the model to converge. And sometimes you need better initial values. So as I said, it could be, it is a solution plane, but it can be also a solution mountain scale. So you want to hit the right point, you have to start from the right point. Like you're hiking the Grand Canyon, you can only have certain points to get into the Grand Canyon. So that's what we say by initial values. So we want to start the model in the right place to get to the final solution. And outliers also make it. Sometimes we'll throw out outliers. I usually try not to, but there are times that you need to, and it's okay to do that. And you can do it in a systematic way. You can throw out really extreme outliers. You can throw out outliers that are, so your fish is in northern hemisphere. You can throw anything from the southern hemisphere, like within reasonable things. Like all you can do is stat-wise. Okay, if you want to just throw out the most extreme 1 or extreme 5, you can still do that. Like, and you just keep running the model. It depends how much patience do you have to do that process. And for this case, it's basically saying anything that's greater than 90 degrees, so anything in space, then we don't want it to be in the model. So that's just some basic R stuff that you do. Or you can just I usually don't pre-filter my file. I only do it in R when I have to run it. I'll just add another statement to say, just like here, you're just saying throw out anything that's beyond 90 degrees, so outer space. And then you can get a combination of these checks, and sometimes you just have to check data because you can be having some issues with longitude. Sometimes some manufacturers don't add the minus, so you'll be at the other side of the ocean, and yeah, that happens.
Tim, sorry.
Yes.
In terms of the, when you said that you can remove or put specific values to try to converge the model. Then how can you compare the model to another model, for example, if you have different parameters set up?
Yeah, that's why I'm saying usually you either use the same set. If you fix something, you might want to compare the same set, or you let the model estimate it. So this when the model,
okay.
Yeah, exactly.
So you can estimate it.
Yeah, and sometimes like usually what I usually would do is I would try to get a solution. Even if you need to fix something, try to get a solution that works first and use those initial values to speed it in. So that's a lot of iterative process that will get to what you want to do, but it's not usually straightforward when you have cases like that. And I'll show you this one case that I worked on. So this is a big eye tuner that was out at sea for 4.5 years. It gives me light data for 4.1 years. So it includes 2 round. So this tag up, I think it's right here. There are 2 round trips out. I don't know where. Not beyond Hawaii for sure, but I don't know where. Maybe near the power buoys over there. So 2 round trips, and yeah, and actually it's recaptured not far from the starting point. And that is one track that I used a whole month to get this stuff. Yeah, so it's like I worked nonstop for 1 month to get this track because there's just too much data to deal with. And yeah, and I don't think anyone will have the patience to work this track anymore. But all of this on this paper is just one tiny figure there. Those 2 lines, so it took me a month. And I was not even on the paper. Yeah, so lastly, so this is just a compilation of some of the published studies out there. The different methods, and you can see there's a range of error in terms of longitude. So that is longitude. You can it hovers as low as 1 degree all the way to 5 degree. Different methods use different things, and so it's not really a fair comparison. But here I just want to show you the range of even with different approaches, that's the range of error you will get. And for longitude, it's much smaller, so you'll be looking at maybe 0.5 or less to 2 degrees. So again, this latitude will have more problems. I think we can skip this one. So there's an earlier work from using the parameters we get from the tracks. Usually is the affection diffusion stuff, and to project for a whole population. So that exercise was trying to look at those free movement parameters for a whole population of tuna that we work with, and infer the distribution of all of them. So it's stepping away from just individuals and looking more like a population process. And the idea being, would there be a year class effect? Would they be going, different year class will have different geographical reach, and that's what this paper is about. And so this one is the southern bluefin tuna with behavior switching mode. So that's basically will show, that method will give you a heat map of how much time spent for, again, multiple fish at this point. So this one step it up from individual fish and doing the population. So that's the next thing you think about. Once you get individual tracks, what do you do with them? And this one is the juvenile bluefin tuna work that we have, and this is just a simple, almost like kernel density stuff, but there's a slight distinction for kernel density plot and utilization distribution, as we would call it. Like kernel density require point process. So those point process should not be related to each other. So there's some issues with kernel estimates, because like we'll be assuming each of our positions to be unrelated, which is untrue. So the methods that Ben has worked on also factor in the error estimates around our track. So we not only consider a track point, but the uncertainty around it, and builds the kernel a kernel-like utilization distribution using those information. So it's include the uncertainty. And this part, this can be done with the package analyze PSAT, which now is part of. It's in parallel with the KF models I mentioned. It's like they're housed in the same website. The help pages. We'll go through part one of them, and it's not difficult to do it. Like we haven't done a formal comparison with the Brownian bridge kernel density estimators. The Brownian bridge kernel density estimator is probably similar to what we have here. This Brownian bridge also have a random walk component in it, and so it's not a point process. Yeah, and that's it. That's our lab website, and let's see what time it is. I think it's now coffee break before, and question and coffee break time. So that's it.
What's the name of the method before?
We call it utilization distribution, UD. It's different from kernel density. The kernel density is so that's why like the terrestrial people, they're moving away from kernel density plots too. They're doing a lot of Brownian bridge stuff. Yeah. And if you want to play with the Brownian bridge stuff, you can look into the library called Move, M-O-V-E. They have kernel density. Brownian bridge kernel density is a mouthful, BDDE. Yeah, Brownian bridge density estimators, BD. Yeah, BD.
There's also like dynamic Brownian bridge.
Exactly. Yeah. Exactly. Yes. That would. I would definitely do that for any spot data that I have.
You would, sorry?
I would do it for any spot data. We'll be doing the Brownian bridge kernel density estimate.
Yeah, better than the kernel.
Yeah, don't do the kernel. That's not trendy anymore.